Hey, good evening all. Today what I've done is I'm trying Overleaf. It's an online LaTeX editor. That is to say, I'm hoping for a setting where I could either type or at least present mathematical formulas pretty quickly for online instruction. And what I have for us today is a dress rehearsal, both for the sake of practicing with math formulae here in typing, and also to just get more of a sense of how this streaming service will go. And scene. Alright, so we just saw a loose derivation of the idea behind the Poisson process and how we could try to get a sense of the timing of the observations. Now, just like what we said during the first week of the semester, when we have probabilistic situations, we cannot pinpoint answers precisely. Instead, what we're hoping to do with these distributions is to have a better sense of them with the expected value and variance. And as you can see here, what we're going to do is derive the formula for the expected value of a Poisson distribution. So I want us to think a little bit more deeply about that. Let's see, where is my code? And what I'm hoping is that we could spend a minute where you think to yourself, what do we need to compute the expected value for a Poisson distribution? So go ahead and spend a few moments on that. For one thing, remember that we're back to using a discrete distribution. So what techniques or what math stuff do we need to compute the expected value? So correct, we need a summation. What else? And we need the probability mass function. We need that formula that we just derived on the previous section, this probability mass function, the individual probabilities. Alright, good job. So now here we will derive the expected value for a Poisson distribution with mean mu. Like you said above, in order to do this calculation, we need to take the summation where we multiply the values, namely the k values, times the probability that we would observe k observations in such a time frame. From the previous section, we have the probability mass function, this funky looking fraction here. And we're going to pretty much use a lot of our mental muscles to try to simplify this summation. So first of all, notice that in the fraction, or the summation in the middle, we have the summation is in terms of k, but we're starting at k equals 0. So if we plug in 0 into this summation term, we simply get 0 back out. And this is a quick argument to say we can actually start the summation at k equals 1 without any loss there. Now, notice also we have a k in the numerator and a k in the denominator. Recall also that k factorial is k times k minus 1 times k minus 2 all the way down. So that first k k in the factorial cancels out, and that's why we're left with a k minus 1 in the denominator. Now, we have seen before that for factors that are not in terms of the summation variable, in this case k, for the factors that are not in terms of k, we could factor that out. Actually, sorry, I think I said that out of order. We have a k here in this exponent and a k minus 1 here in this denominator. It would be great if that lined up a little better. So we're going to do something mildly clever and separate the mu's. Take out one of those mu's, so we have mu times to the k minus 1. Quickly verify those would add right back up to mu to the k power. Now that this exponent and this denominator line up, it will lead us somewhere. This will bring us back to that earlier point about factoring out the factors that do not have k in them are constant with respect to k. Now looking at this summation with the k minus 1s, and we happen to start at k equals 1, it turns out that starting point could be a bit arbitrary. We could move around the starting index as long as we compensate for that later or elsewhere in the summation. So here, this summation at the bottom, just kind of take a moment to verify that if we plugged in k equals 0 into this simpler summation, it would be the exact same thing as if we plugged in k equals 1 into this second to that summation up here. That is to say, these two summations are the same. It's just simplifying or rewriting where we're starting the summation. Alright, remember I just said we're trying to simplify this summation, and we're hoping that this all does simplify. So my broad question to you is, with all your experience in mathematics, does this summation look familiar to you? I'll give you a minute there. Okay, so someone in chats was correct that that's the Taylor series for e to the x. That is, if we have this formation variable to the n power divided by n factorial, that's what we saw in second semester calculus. Here in today's material, it's pretty much the same summation, but in terms of mu and k. Alright, so good job on noticing that observation, and therefore we can now simplify this summation, realizing that last part is simply e to the mu power. And what we're left with is e to the negative mu times e to the mu. Those are literally inverses of each other. They cancel out. Therefore, it turns out for the Poisson distribution with mean mu, the expected value is also mu, which is very pleasing when you're trying to describe the Poisson process and the expected value of observations in a time frame. And scene.